Yeah, I think that's all. Okay, let's start with today's topic. It is just an extension to what we did last time. So, couple notes before we start. I've seen some people from the last in class yesterday, when they wanted to find this theta, what they did, they wanted to do trig here to find the theta. The reason why this is wrong, because within the beam span, you have a curve, you don't have a line. And at each point on a curve, you're going to have a tangent that is different. So the reason why you can't use trig here, instead you use the equation, because if you use trig, imagine you make a curve, you make like a tangent here, and then you have this, you need to close the triangle, right? So you are estimating a very big deflection that is not real, okay? And you're also getting a very big angle that is, I mean,
it's an approximation.
so no, the curves on the table is not approximation. So the equation, you're gonna develop them in advanced classes. All this conjugate beam method, moment method, you're gonna develop it. So the point is, when you do the trig, at the very first point here, you are estimating a very big deflection that's not real. That's why we only do trig at location, for example, like what we did in this example, here. So the load stopped here, so there is no need, or there will be no, for example, it will not be curve anymore, it's gonna be some sort of straight line. And we're gonna demonstrate this now, but I just want to highlight this. One more thing, and all this is from the last time. So the theta that we are only interested in, it is the one at the ends, whether we have simply supported beam like this, so we are interested in those theta, or we have a cantilever, so the theta gonna be at the end, because the theta at the beginning here is equal to 0. And that will be one of the MCQ questions. I'm gonna give you like an end condition, I'm gonna tell you what is the theta and what is the deflection. I don't wanna see any calculations. If it's 0, just put 0, okay? I can't hint more than this. Anyway, but what if someone might want to find the theta here at this point? Anyone can tell me what's the theta here? 0, that's correct, because the steps is you make a tangent to the curve here, and the angle from the curve, from the angle from the tangent to the original axis of the beam. So the axis of the beam was also x, so they coincide on each other. That's why at the maximum deflection, you have a 0 slope deflection, 0 theta. Is that clear? So now, do you all know when to use the triangle thing, and when do you stick to the equation of theta, which is PL squared over 16EI, which is not a straight line, it's just like a curve. It's a function of L squared. So it's a parabolic, it's not just a straight line like this, because you're overestimating the deflection. So moving to today's class, or before moving, I changed something in the beam table. Most of you noticed this last time, that there is a typo here, and this should be a theta 2. So you may correct this in your table. But don't worry, because the tables, I'm gonna attach it to the exam. So you don't need to write any equations or anything. This 2 pages is gonna be attached to the exam. Okay. Moving to today's, we have beams with overhang, or we can call it beam with cantilever. So beam with cantilever is more practically said. I haven't heard beam with overhang until I came here. I don't know if I'm pronouncing it even correctly or no, but let's call it beam with cantilever. So beam with cantilever, the definition for it is simply supported beam. That's not the full definition, but I just want to divide it to just explain a couple concepts here. Simply supported beam. When I say simply supported, I maybe didn't explain this in details last time, but simply supported means you have a beam and you have pin and roller at both ends. That's the definition for simply supported beam, which means we have a beam and it's supported at both ends. But continuing this definition, for the beam with cantilever, I'm going to say simply supported beam, but I want to say but continues beyond the support from one side or both. What I mean with this is the same simply supported beam. I'm going to copy it 3 times, and the cantilever can be from one side like this, okay? It can be from the other side, or it can be from both sides. And the last one, we call it practically, it's a beam with double cantilever. But just for the sake of this class, beam with cantilever, it covers all the 3 terms, okay? You already are experts with the table, so you all know that none of them are on the table. None of these conditions are on the table. So we're going to do some maneuver here based on our understanding of this. So let's say this guy, I'm going to copy it, and I'm going to say if I have a point load in the middle, how the cantilever part gonna bend. And also, if I have this beam with double cantilever, and I also have the same point load, how the both cantilevers gonna bend. We're gonna demonstrate this now, and I will have you to conclude it for me. So I need a volunteer to come just to put a finger in the middle. Anyone? You can come. Yeah, it's oh, it's here, okay. Come this side so that they can see it. So my hands are the supports. It's preventing the beam from falling. Do you see what happens at the end? It doesn't go from the middle push. It is a curve. And what's happening at the end? It is just a straight line, okay? That's if I have beam with one cantilever. What about beam with double cantilever? Put your load in the middle. What happened at the both ends? It goes up. So with this, thank you. With this, what I'm proposing is, for the middle part, you're going to use the table. So we know from the table, as you all, I'm sure that you know how to use the table now. For the middle part, you're going to use the table. And whatever extended from the beam, you're just going to extend a straight line, like this, with the same slope that the curve ended with, okay? So what if I have, this is for the single cantilever, what if I have both cantilever? And I'm stressing on this again, the line gonna extend with the same theta here. So I'm gonna extend it like this, and I'm gonna extend that one like this, with the same theta. Is that clear? So this is how we can draw the elastic curve for beam with cantilever. And drawing this elastic curve or deflection is important, and you're going to see in the exam. I will ask you draw the elastic curve for beams. And basically, those beams going to be from the table. But of course, I'm going to play with the direction of the load. But it's going to be a straightforward. Okay? So let's do an examples of how we can approach this. So I have now beam with cantilever, and I want to find the deflection at point A here. So point A is at the end of the cantilever. And again, we don't have this condition in the table. And I missed one of the conditions. You want to come again? You want to come again? I'm so sorry. I want you to put your hand here just for you to imagine, because once you imagine this, put your hand. Yeah, harder. What's happening in the middle? What's happening in the middle? It's going up. Thank you. So I want you to do this, so you don't have any excuse now when I ask you to draw it and you leave it blank. Don't leave it blank. So the cantilever, if I have a load at the cantilever, it's going to affect the beam span, okay? But again, we don't have this loading condition in our table. So what I'm proposing here, I'm going to say I want to find the effect of this beam, of the cantilever part, with the distributed load. And this case is on the table, and it is case number 10. Okay? I have 4 kip over foot, and the deflection for this cantilever part is going to be something like this. Okay? And you're going to get the V. But here comes the question. Is this assumption right? What I did wrong here? What did I assume wrong? That there is a fixed point. And what is the fixed point? What is the difference between the fixation and the hinge here that was originally in the question? Moment. So what we did here, our assumption was we disallowed the rotation when in the real example, we have a roller which allows rotation. So after getting this V from this case, we're going to do a correction case. But let me do this V first, so we have all our numbers. So let me call this V1. So V1 from the table, it is WL power 4, 8 EI. And I've seen it yesterday. Some people would multiply 4 times 12 to convert it to inches, but no. 4 is kip over foot. So the foot is at the bottom. So you want to multiply the bottom by 12, which makes it 4 times 1 over 12. Okay? And then the length, don't take, which is a common mistake, the length of the beam. Look at the table. The table tells you to use this equation, the L should be the length of the cantilever. I don't want any of you to get the total length. Use the length that's specified in the table. So the length here is 8 foot times 12, and then 8 EI. And I just have the EI as a 1 number here, which is 898,570. When I calculated this, I found the deflection is 0.357 inches, and it points down. This is incomplete. We need to fix the condition that you all said, that we disallowed the rotation here. So what we did, we initiated a bending moment reaction here, which wasn't there in the real problem. So what I'm going to propose now, I'm going to initiate a load case, which is a correction load case, which takes into consideration this bending moment. What I want to do, I want to find, as if I remove this cantilever, and I want to find the moment that will come from it, and I'll be putting it here. So that this bending moment, it is counterclockwise, it's gonna cancel that one, and that one which is clockwise. So this is the reaction. So you can either find this bending moment reaction and just flip it here, or like do the opposite direction here, so that when you put this on that, they will cancel each other. So this bending moment, I'm gonna do it directly here. It's gonna be M is equal to, as if I want to find the bending moment here, as if I'm taking the bending moment at this point. So what I'm going to say, I'm going to say 4 times 8. So I have a point load now. Multiply this point load by 4, which is half the distance, and then I have a bending moment here. So this bending moment is going to be 4 times 8 times 4, and it's equal to 128 kip foot. Okay? Now this load case, you have it in the table, and it is case 3. Okay? But again, don't forget, what we want to find was the deflection at the very end here, which is point A. So from what I explained earlier, can anyone tell me how can I get the deflection at A from this load case? Case 3, and what you're gonna, when you go to the case 3 on the table, what would you do? Find the theta, and then just make a straight line. So this load case, it is case number 3, which is here. And case number 3, you have a clockwise moment, and clockwise moment, it causes deflection that goes down. If you want to think of this moment or this arrow as your thumb, and your thumb is pushing the beam. That's why it's bending that way. But if the thumb is from down to up, it's bending the other way. So I'm going to find the theta, this theta, which is right next to the bending moment, which is ml over 3ei, which is here. I'm going to draw the elastic curve first. And once I reach the support, I'm going to have a straight line like this. And this straight line going to have the same theta as the curve ended. So this theta is equal to that theta from math. I don't know. I don't know the name of this condition, but you all took it in high school, right? So when you have two lines like this, the theta should be equal. So the theta is ml over 3ei. The moment, what we did before, which is 128 kip foot, here we multiply by 12. We're not going to divide it by 12. And the length, what do you think, what length should I choose? 22 times 12 over 3ei. Okay? And you're going to get the theta is equal to 0.0136 radian. And to find whether it's clockwise or counterclockwise, here is the beam, here is the original position, and the beam deflected or rotated counterclockwise from its original position to the deflected shape. Okay? That's why it's counterclockwise from here and still counterclockwise from here as well. So I'm going to say this is counterclockwise. Okay? Now, to find the deflection at this point, I'm going to focus now on this triangle. What do I have in this triangle? I do have an angle, that's correct, and I do have this length, which is 8 foot. Okay? It's not cosine, because cosine is the, it will be tangent. Cosine is adjacent over the hypotenuse, and we don't have the hypotenuse. It's unknown. And we are not interested in the hypotenuse. We're just interested in this. Okay? I said last lecture, I want to correct it. I said tan inverse, the theta. It's incorrect. It shouldn't be inverse. It's just tan. So tan theta, which is 0.0136 converted to degrees, which is 180 over pi. And if you try this in your calculator, if you plug this in your calculator, tan 0.0136 times 180 over pi, because it's small, it's going to be equal to 0.0136. So what I'm proposing here, don't do the tan. Just take the angle as it is, and then say this angle is equal to the opposite, which is the v that's unknown. Let me call it here v2, over 8 foot, which is 8 times 12. Did I lose anyone? I lost you? All good? Okay. So the V2 is going to be equal to 1.3 inches, and it's pointing down. Now, I do have the deflection from case 10, and the corrected deflection, I just corrected it by adding the right amount, because when I restrained, yeah, we're going to add them. What I did here, I restrained the deflection. So if I'm just holding it like this, because the fixation doesn't allow any rotation here, it's going to bend a little bit. But if I allowed rotation, it's going to go down. So I'm going to add both of them, and this will be the final deflection. It will be 1.3 inches, and it was pointing down, plus 0.357, and it's pointing down. And the solution here is going to be 1.66 inches, and it's pointing down. I have another question for you. What if I asked you calculate the deflection at point B, which is at midspan? How many load cases do you think we should use in here? How many? Not what load case. How many load cases should we use? Just one, okay. And which one should we use? Case 3. That's correct. There is no need to do case 10 now, if we want to find the load at the midspan. So to find the deflection, at the midspan, we will use this load case because we took the effect of the cantilever by adding the bending moment. So we're going to use this load case, and no need to do any extension here. And from the table, we can find the deflection in the middle. Common mistake. If I want to find the deflection in the middle at B, some of you will go right away to this equation, which is Vmax. Why is it wrong? Anyone? Why is it wrong if I want to find the deflection in the middle here to go to this Vmax? That's correct, because Vmax isn't in the middle. Vmax is only correct at this condition, which is L1 minus root 3 over 3, which is less than the half. It's not at the midspan, it's half. Okay? So instead, you'll go and use this general equation, which is valid at any point within the beam span, along with that one. Okay? So another example, what if I added a load at the midspan, and I ask you the same question, what is the deflection at point A? Any suggestions? What should I do? Okay, I'll do the same thing. Okay, so if I use case 10, immediately you're going to take case 3 with you, because you want to correct the assumption of this allowing the theta. So now I'm going to take both of them. That's correct. It's not correction now. It is just it just added to that. So, like you said, I'm gonna do another case here, which is case number. This is case number 1, and it will be a beam, simply supported beam like this, and I have a point load in the middle. And just from the table, you're gonna draw the deflection. It's going to be something like this. And to find the overhang part, or the cantilever part, we're just going to extend this line like this.
Don't you need to correct that too?
Why do we need to correct that?
Because isn't there a moment there as well?
But we took it the moment here. So the only correction that you need, if you assumed something like this, so you assume that the theta is 0 here, when it's not 0. That's why we did case 3. But here, we didn't do anything wrong. It's deflection, and due to that deflection, we are extending it. Tell me.
So we're just adding that deflection to what we already added?
That's correct. So from both of them, what we got earlier, from this 2 load cases, we got this one, which is 1.66 looking down. So V is 1.66 inches looking down, or deflecting down. And again, no need to put any signs, either like whether it's in deflection or the rotation, just pointing up or down, and whether it's clockwise or counterclockwise. So what you're going to do, you're going to get the theta from here, and this theta is going to be equal to that theta, and you're going to do trig in that part. Okay? Just for completeness, I'm going to give you the theta. The theta is PL squared over 16 EI. And if you substitute, you're going to get 0.0198 radians clockwise. And then you're going to take this small triangle out. You have the theta, you have the 8, and then you have the last V that you need to add it to the total V. And there is no need now to write the tan, because you all know now, I'm just going to take the angle, which is 0.0198 is equal to V over 8 times 12, and the deflection is going to be equal to 1.9 inches, and it's pointing up. And it makes sense because the cantilever load want to force point A to go down, but the 45 kips in the middle, it's trying to have the point A goes up, okay? So after getting this last V, some people will leave the paper and just leave. No, to take the full credits, you need to have the V total, which is 1.66 inches pointing down, minus 1.9 pointing up, okay? And you're gonna get 0.23 inches pointing up. And a practical use to this concept, when I do have a beam with cantilever, and this is very common, the load on the cantilever will force the last point in the end of the cantilever to go down. And from the table that I showed you from the American codes, from the last lecture here, this table, you don't need to write it or anything. It's just for you to know. I don't know if the cantilever here mentioned, but for cantilever, perhaps there's another table for it. No, the cantilever is not here. But for cantilever, you have a very strict deflection limitation. So some of the ideas that you will somehow, if you have a very large deflection, and it's unsafe in terms of deflection, not strength-wise, it's just deflection, some people would add a load in the middle of the span just to reduce the cantilever's deflection a little bit. And this load can come into just a heavy dead load, which is like a heavy flooring or a heavy, for example, people who went in construction, if this is concrete, before you put the last layer, which is the, I don't know, the flooring, there is a sand, there is a lot of material. So you might consider adding more material to make this heavy a little bit so that you might reduce the deflection at the end. Because if you added load here, what's happening at deflection? And this is also popular. Sometimes we are intentionally adding deflection. For example, I'm not sure. 1 minute. I want to say long span bridges. I'm just going to search for it, and very popular in that. I want you to notice, I don't know if you see my screen. You see it, right? I want you to notice that sometimes we are adding a deflection in the slab itself. So the bridge itself, we are forcing the deflection to be up like this. Why is that? That's correct. Because when we add load, if it's straight like this, when we add load, there will be deflection already. But if it's already deflected up, which is like as if we are, these cables, we are just like applying tension a little bit harder, it's already coming, like it's already deflected when there is no cars. But when there is a lot of cars, when there is people, like if it's like a revolution or anything, or in case of wars, you have a tanks that will go in there, and this bridge will be full of tanks. That's when it's gonna straighten a little bit, or it might deflect down. But this deflection counts as like a counter deflection, if you understand what I mean. And sometimes we do this in building. In case this beam, like a very long beam, we might pour the concrete in a way, we will design the formwork of the beam to be like this. So that when we put, but it's not gonna be so much, but it's gonna be enough, and it's be calculated so that when we put the lead loads, the shears, for example, and the flooring, it is enough to deflect it to become straight, okay? Because you don't want to walk on a beam that's like this. Is that clear? How we can use the deflection to serve like the safety of the structure. Okay. Lastly, what if I have Oh, before this, I didn't say what if I have, if I ask you, what is the deflection at point B? So what is the deflection now at point B? So what load case should I use? How many load cases now? 2. That's correct. Not one case. It's yeah. So you're gonna use this load case, which is load case 3, which you have a bending moment that takes the effect of the cantilever, in addition to that point load. And now you don't need to find the theta or the triangle or anything because the deflection at the midspan. So you're gonna use this part, and you're gonna use this part. Find the deflection here. This is the Vmax, so it's straightforward. Here is not Vmax, so you're gonna use the big equation, and just add them together. Any questions?
So you have to correct it again if you're solving for something like that.
Okay.
That's kind of what I meant before when I asked if there would be another correction case.
Okay, let me tell you something. This load case will serve as a correction if we assume this. But if you're not interested in this load case, it is no longer correction. It is just a must because we want to take the effect now of the cantilever. So
Correction, but you still have to take it.
that's correct. Did I lose anyone? All good? Okay. Last thing to make sure that you understood everything. How many load case should I do to get point A? And how many load case should I use to get point B? Let's start with how many load cases for point A. Anyone? I heard 1, and I heard 2. I heard 2. So whoever said 2, why 2?
There's no need for 3 because there's no load on the cantilever. So you need,
So what the 2 load cases that you're proposing?
the ones we did before.
Okay, which one of those 3?
So it's going to be case 10 and.
Why case 10? Do we have a distributed load on the cantilever?
No, right.
So how many?
Just case 1.
Just one case, which is that one only. Only. The reason why there is no load case 10, because what load should I put on the cantilever? And if there is no load on the cantilever, I don't need to do any correction, which makes eventually, for load case A, I'm gonna take that one only. And get the theta, get the V, and that's all. Okay, now what about B? Deflection at point B, which is at the midspan now. How many load cases do I need? 1, and which one? And it's load case 1. So you're gonna take that one for load case B, and I don't need to do the extension part, and I don't need the theta. It is just at point B, which is at the midspan, you're gonna use the Vmax equation.
What's the difference from the one that we just did above when it was 2?
Here, for example, here, you wanted to find B, right? So B, we're gonna use that one because we already have point load in the middle, so there is an effect that the point load will do. In addition, when I have a beam with cantilever, if I have a load at the end, it's gonna affect the midspan. That's why if I have a load at the cantilever, I'm gonna take case 1 and case 3 to find the deflection at the midspan, which is at point B. But the difference now, for point B here, we don't have loads on the cantilever. That's why we're just gonna take this load case, and it's good. So this 3 examples is very important that you understand when to use the correction, when to use the effect of the cantilever, and when just to put one load case and call it good.
There's no weight of the cantilever.
Okay, that's right. In real life, the beam itself has a weight. So this weight, it is like a distributed load all the way, but for this class it's not a design class. It's just analysis. So we are neglecting the weight. If I didn't give you the weight, and I'm not gonna give you that because I didn't prepare you for this, because it is already in the design classes. So there is no need. We just focus on just the external loads. We don't focus on the beam weight itself. Any more questions? Okay, that's all what I have, and we finished early today. And I'm going to see you next week.